Hey everyone, it's Tesla Tom here from Ludicrous Feed, and thank you so much for joining us. In today's video, I'll be going through the V2X.au summary report on opportunities and challenges for bidirectional charging in Australia, dated 30th of June 2023, prepared by NX for the Australian Renewable Energy Agency, otherwise known as ARENA. Alright, let's get into it. Alright, so first page is the disclaimer, and this report was commissioned by the Australian Renewable Energy Agency, ARENA. And it is basically a snapshot of the status of the opportunities presented by V2X, and we'll find out what V2X is very shortly. Okay, so it is particularly for the Australian market, of course, and particular focus on residential and light commercial vehicle to grid or V2G applications, and findings in this report are based on interviews with national and international supply chain stakeholders and cash flow modelling for 24 residential customers across the national electricity market. And this figure here is an estimated gross energy storage capacity in the NEM, or National Electricity Market, in 2050, which is in 27 years' time. As you can see right there, EV fleet battery capacity is 2,359 gigawatt hours in 2050, and the total NEM storage requirements is 640. So if you tabulate all the energy storage in EVs in 2050, it far outweighs the requirements for NEM, or the amount of energy required by people in 2050 in Australia. So let's go through the text. So basically, yes, bidirectional EV charging represents one of the largest potential enablers of Australia's energy transition. As I said in this graph here, the NEM in 2050 will require 640 gigawatt hours, as estimated in 2022, as shown in figure 1 here. And the usable storage in Australia's EV fleet at that time will be nearly 4 times the requirement of the NEM. So flexible bidirectional charging will form from only 10% of this capacity, could provide 37% of total NEM storage needs, offsetting around $94 billion of large-scale battery storage investment. So that's good to see. So by the early 2030s, which is next decade, EV fleet battery capacity is likely to surpass all other forms of storage in the NEM, including the Snowy Hydro Scheme 2.0. The near-term capital cost premium for enabling V2G is estimated around $25,000 per megawatt hour, or 6% of current large-scale battery costs on a simple per megawatt hour basis. The basis of this is that the cost of enabling V2G is only a small marginal increase in the cost of installing a V2G capable charger. So compared to installing a normal charger, the additional cost is very small. The battery does already come with the car. Compared to other jurisdictions like Germany, Netherlands, South Korea, and California in the US, Australia does not have a policy framework to accelerate the supply of bidirectional charging equipment. In some ways, our complex and opaque framework for technical standards and regulation makes Australia one of the hardest developed economies for international OEMs to enter. And so this report is hopefully going to help straighten things out. So key findings. Number 1, Australia's EV fleet will be the largest and lowest cost potential storage resource in our energy transition, because the battery's already there in the car. Wide-ranging measures are needed to make most of this opportunity. National EV policy should signal that we value V2G and V2 Home or V2B as a near-term priority. Australia will be left behind in the early stages of global growth in V2G due to our limited engagement in international standards. Okay, so we do need standards, and government and network businesses can play more active roles in doing this. Current standards can be addressed immediately by the Clean Energy Council, agreeing to a more permissive interpretation of the standard. Formal V2G functionality in OCPP remains under active development. Okay. Network tariffs can make or break V2G. Networks should collaborate to develop more V2G supportive tariffs. Currently, there are basically none, to help national coherence to international supply chain stakeholders. Number 6, V2G is most valuable when exposed to wholesale spot pass-through arrangements. And number 7, ARENA should consider funding V2G supply chain facilitation initiatives, while also investing in early commercial trials. Okay, let's go through it right now. Okay, so there are the contents right there, and acknowledgements as well. And okay, so let's go through some of the terms. Like I said, this report is quite high-powered. We'll try and make head or tail of it by breaking it down for you. So V2X is the new term, I guess, or the all-encompassing term for V2L, V2G, V2B or home or building, V2H, V2B. So while V2L is easily identified by general purpose outlet being located inside or outside the vehicles, there is no internationally agreed way of differentiating between other V2X types. So we've seen V2L in our channel. Some of the EVs right now can allow V2L very easily. BYD Atto 3 and the EGMP vehicles like the Hyundai Ioniq 5 and EV6 from Kia. So in this report, they differentiate V2H, V2B, and V2G by the configuration of infrastructure external to the vehicle, meaning the underlying capabilities of the EV being essentially the same. We refer to V2H, V2B where the whole electrical system is islanded from the grid. Conversely, V2G, or vehicle to grid, is grid connected and coupled with the prevailing AC grid frequency, 50 Hz. Whether or not the generating system is coupled to the grid has important implications for the electrical design, of course. So, like photovoltaic solar panels, EV batteries produce direct current DC and generally needs to be converted to AC prior to use. This conversion can occur within the vehicle itself using the onboard power converter or via an external power converter. So, Figure 2 provides sort of a grid of V2X types used in this report, and Figure 3 has a high-level summary of the technical characteristics and example consumer use. So compared to V2G, V2 home building has a much more limited application and economic value for mass market grid connected vehicles, of course, customers, of course. However, it is important not to understate the value of a backup power supply into areas of poor electricity network reliability or in remote locations where the cost of establishing a grid connection is prohibitive. So Australian consumers may also like the idea that they can be more independent from the grid. That's V2G. Okay, so let's have a look at Figure 2. So we've got grid islanded systems like V2H, V2B, or home or building, where the power converter is external to the EV, or you've got an onboard power converter in the car, so you can have AC, V2H, V2B, or V2L. Whereas grid connected, which is V2G, can have a DC or AC system depending where the converter is, whether it's external to the EV or onboard the EV itself. So V2X categories such as V2L provides the grid forming AC power through general purpose power points inside or outside the vehicle. The power converter is on board already. So we've got examples where charging electronic devices while driving. The outlet is inside the cabin. That's quite available already. We've got USB ports everywhere through a lot of EVs. I would say almost all EVs. Mobile generator for selected appliances. Yep. And backup generation for selected appliances like refrigeration during a blackout. AC V2H V2B provides grid forming AC power through to a building electrical circuit that is islanded from the grid. The power converter is on board, whereas DC V2H V2B there's an off-board inverter that then converts the grid forming AC power to a load. Electrical system is islanded from the grid. Then you've got AC V2G and that provides grid following AC power through an electrical circuit that is coupled to the grid, and the power converter is on board. And then you've got DC, basically where the circuit is grid connected and it's off board. So I guess in summary, AC is generally where the power converter is on board in the car already, so converting the battery DC power to AC before being able to use practically, whereas DC, the power is off board, so outside the car for use. Alright, let's go through more of this document now. So page 6. Okay, so some more terms here. V2X requires a working confluence of several relatively independent standards, so they go through all those standards there. And the more details in table 1 again, of course. So the timing of proliferation of V2G requires these standards to be sufficiently mature, permissive, and aligned in any given market. Achieving this is a current global priority. So very few markets have their market regulatory and policy settings fully resolved. Not very many. US and EU markets are currently converging in some areas to accelerate V2G adoption. There are many differences in standards across these markets. There are similarities and some convergence in relation to small-scale inverter standards across the regions, including Australia. So some interest in AC V2G in the US has renewed efforts to finalize standards driven by EV OEMs. That's good. So OCPP is the de facto means of controlling EVSEs, or otherwise known as EV chargers, by remote agents. OCPP is being incorporated into future versions of the standard and is already mandated in Korea, California, under the US National EV Infrastructure Funding Program, otherwise known as NEVI. Okay, upcoming OCPP 2.1 will formalize V2G control and is only backward compatible with 2.0.1. So while the OCPP 2.x family is being developed with some consideration of Australian requirements, this functionality is not yet finalized. OCPP does not specifically provide for Australian use case, such as dynamic tariffs, dynamic export limits, or AEMO specifications for frequency control. Okay, so more issues with standards there, which they'll go through. Okay, so let's go through the next page. Standards testings once again. We've got debugging there. Some markets provide test labs where EV and EVSE OEMs can test and debug equipment, and certification, a process by which an independent accredited body assesses if a product satisfies the requirements of formal standards. That's important too. Okay, so typically EVSE is certified in dedicated e-mobility certification labs. More about certification here. And conversely, specialized facilities can help debug or certify compliance. So compliance certification is important for good standards. Australia is perceived as very mature in our approach to testing and certification of EVSE. So these issues are reported by international OEMs as an impediment to local market entry, which means Australia is likely to lag behind other markets in relation to V2G compatible, capable product supplies, competition, and price reduction. Reasons for this are, unlike some major overseas markets across the world, like UK, EU, UK, Korea, they've got UK twice, Korea, India, etc., Australia has not standardized many key aspects of EVSE design. For example, CCS. As a result, there is no definitive Australian specification for an EVSE, which is a shame. There are some local requirements are defined. Parties bringing V2G products to Australia assume higher risks and costs where there are more standards. Also, there are limited testing facilities for local and international OEMs to debug smart and bidirectional EVSE against Australian use cases, whereas other markets provide access to test pre-commercial EV and EVSE for free as an industry development measure. So examples of EVSE test labs, so DEKRA and ELAD-NL as well, which is a Dutch grid operator partnership. Okay, let's keep going. Page 8. So V2G via different charging types. Okay, so this is an example of what can happen here. So mode 2, where the EV is connected to an AC grid through a cable, incorporating protection and charging control infrastructure. It says here mode 2 cannot be supported in Australia and New Zealand for that matter, for V2G, V2HB, because of requirements which prohibit two-way power flows through standard power outlets. In effect, this means V2G can only be operated through an EVSE that is hardwired to an electricity mains, so therefore mode 3, mode 4, whereas mode 3 is where the EV is connected to an AC grid through a hardwired EVSE for protection and controlling infrastructure, and mode 4 is where an EV is connected to an EVSE through DC, and the EVSE itself handles the protection. So basically, mode 3 is where the converter is on board, whereas mode 4 is where the EVSE is the one that's converting and handling the protection and charging control. More about regulatory frameworks here. Okay, let's keep going. So, V2, where is it up to? Done that one, and we've done this one and this one. Alright, so V2H, V2B, V2, we've got trials here, so international trials. So V2G Hub is a global database, 117 projects worldwide. Europe is the global epicenter with over 80 projects started since 2009. By contrast, Australia and New Zealand have only 2 recorded trials, including ActiveWaggle in the ACT and Vector's V2H trial in Piha, New Zealand. Okay, so fundamental benefits of V2G, V2HB are well established. Capabilities are well demonstrated in relation to frequency control, time shifting, and grid service. Majority of international trials have used R&M Alliance vehicles that employ the CHAdeMO standard. Okay. However, industry is shifting to CCS2 based V2G, and this hub has at least 11 CCS-based trials covering over 350 charge points. Further industry experience in the use of CCS will help, definitely. Yeah, we're certainly seeing more CCS charging ports and plugs in Australia. Policies to support V2G. So in many jurisdictions, policies to support V2G uptake remain focused on funding, proof of concept, and early commercial trials. Reflects nascent supply of capable vehicles, especially those using CCS. This is expected to change rapidly in the next 12 months. Okay. And a wider range of bidirectional chargers are also expected to be available at that time. Okay. And NEVI is expected to supercharge a shift to the standard. All publicly funded chargers needing to have that capability from 2023-24. An example of California's bill there that require that beginning in the model year 2027, all new EVs sold in California be bidirectionally capable. Okay, maybe that's why in the recent Tesla earnings call, or I think a couple of earnings calls ago, Tesla did make it known that they'll be bidirectional soon, including school buses and light-duty vehicles. Okay, there we go. And this is where all the trials are, as the report said. The majority seem to be in Europe. 80 of them out of the 117 trials at the moment going for V2G or V2HB. This is what I'm interested in. So EV model availability. Australia sits at the end of international EV supply chains. Today, only Nissan and Mitsubishi, both part of the Renault Nissan-Mitsubishi alliance, have supplied V2G capable vehicles in the Australian market. Since launching in 2012, Nissan has sold over 2,000 V2G capable Leafs in Australia compared to 600,000 globally. V2G capability of these vehicles largely sits dormant, limited to trials, and due to local barriers for bidirectional EVSE certification and listing. A much wider range of vehicles will become available over the next 2 years. As shown in this figure here, 36 models in the European market have been announced as having current or future V2G capabilities. Of these, 11 also have AC V2G capability. So most of them are actually DC capable. The battery capacity of V2G capable vehicles is typically larger, 20% overall, and the models are more expensive, 11% overall. The premium brass and larger battery size is considered coincident and related to product marketing rather than any underlying technology requirements or additional production costs. Interesting. So mostly increased due to marketing rather than actual technological requirements. The incremental hardware cost required to enable V2G at DC level is negligible, much less than other advanced features like plug and charge, and principally associated one-off testing and certification. Conversely, AC V2G requires an onboard power converter that is compliant with local grid codes. While this can add cost, weight, and volume to the vehicle power electronic system, AC V2G is considered supportive of automakers adopting more integrated service models, providing them with more direct access to operational revenues. So V2G DC is negligible to scale up as opposed to AC onboard V2G. New EVs in Europe will use CCS2 plugs to enable V2G, as will Australia. Okay, this timing aligns with announcements by automakers such as Volkswagen, Skoda, Polestar, Volvo to unlock V2G capability by 2024. It's not far away. That's next year. Here we go. Tesla has announced plans to bring bidirectional functionality to all its vehicles in the next 2 years, as I said earlier in the earnings call, and reducing the overall cost of power electronics to the vehicle. Row EV is an Australian company that converts popular ute models to electric, as shown here. It is currently working to integrate DC V2G into the next generation of its Drive Power Electronics platform to release to existing customers by 2023. This could make Row EV utes among the first CCS-based V2G capable EV models in the Australian market. That's great. Summary of EU homologated models with announced or available V2X capability. It's all here. There we go, worldwide. Audi, BYD, Cupra, Genesis, Hyundai, Kia, Lucid, MG, Nissan, Polestar, Skoda, Volkswagen, Volvo, and Xpeng from China. Here we go. Factors driving V2G capable vehicle supply. So dependent on global automaker decisions regarding timing of V2G capability activations. Decisions will be shaped by overall supply of vehicles to Australia, which is growing rapidly, automaker perception of the underlying financial value of V2G in Australia, the ability to capture it, and consumer readiness to engage in innovative new service offerings, and the receptiveness of Australia's policy and regulatory environment, including in relation to the ease of certification and regulatory approvals. So lots of factors there to see the growth of V2G in Australia. Okay, so we've got configurations of EVSE here. So AC, the vehicle is export AC capable. EVSE passes through the AC power to an electrical mains. In the case of V2G, the vehicle needs to have an inverter system that meets the relevant grid codes, cost considerations, minimal hardware cost to EVSE. For the system or the grid, EV must have grid compliant inverter. DC AC, the vehicle is DC export capable. The EVSE converts the power to AC and supplies it to an electrical mains. Inverter must be compliant. Okay, so this is where the EVSE must have grid compliant inverter, and the EV remains the same. No inverter required. And then DC-DC, where the vehicle exports the DC, EVSE passes the DC power to a hybrid inverter for conversion to AC, either directly or via DC bus that can be fed by other DC power sources like solar batteries, etc. So EVSE minimal hardware costs, no EV inverter requirements, but the home, I guess, or the building requires a separate hybrid inverter. Okay, so NX has identified at least 21 EVSE OEMs that are developing bidirectional chargers in the European market. Most of these appear focused on DC AC chargers suited to DC V2G capable vehicles. This aligns with the general expectation among EVSE OEMs that European and Chinese automakers will seek to reduce vehicle costs by utilizing external power conversion equipment. So they keep the EVs the same. US market has great interest in AC V2G, indicating AC EVSE may become more common there. While high upfront costs are associated with development and testing, underlying costs of building a DC AC charger at scale is similar to conventional hybrid inverter plus galvanic isolation and charge cabling. One international OEM reported that at-scale bill of materials cost for a DC AC bidirectional charger is about €550 or 895 AU. By 2026, they're estimating several 5 kilowatt or greater V2G capable DC AC chargers could be available in the Australian market at around $3,500 plus installation and cable costs. Prices have the potential to drop as low as $2,200 in the longer term with strong competition between EVSE. Yes, competition always drives prices, of course. Look at this. So most OEMs are actually developing DC AC chargers. And this is just to refresh your memory. So DC AC chargers are where the EVSE is the one taking the load, and the EVs remain the same. There's no inverter in the EV. It's all the EVSE doing all the hard work. So look at this. So ABB, some of the brands we know: Delta, Enphase, Ford, Costal, InCharge, Wallbox. They're all doing DC-AC, and not many there. Delta is the only one doing AC-AC that I know of in this category. So interesting times ahead. So the opportunity for Australia. So support for Australia's energy transition. The bidirectional EV charging represents the single biggest flexible and as yet untapped resource in Australia's energy transition. Figure 14 on the right illustrates this point, with the total storage capacity in EVs outstripping all other forms of storage in the NEM by the early 2030s. So there we go. So the black is EV fleet battery capacity from 2030 onwards. From 2024, next year onwards. So they're saying that, so Snowy Hydro will basically take up most of the slack once it's up and operational. But then as the EV battery fleet grows, it'll take up the majority of the storage required for Australia's NEM by 2050. Interesting. Okay, so a number of international studies have explored the role of V2G. One study in 2022 demonstrated EVs batteries could satisfy short-term grid storage needs in most regions of the world as early as 2030 at a fraction of the cost. It's good to see. Because I guess, as we've said many times, the battery's already in the car. Compared to other markets internationally, several factors suggest Australia has the potential to become a relatively rapid adopter. NEM is an extremely dynamic wholesale electricity, high prices, variable retail prices, dynamic network constraints, all of which increase the value of flexible resources such as V2G. Market signals to support flexible storage can be expected to intensify with the irreversible trends towards wind, solar, and electrification. Good. NEM framework ready to facilitate DER participation in lots of acronyms here. Introduction of dynamic operating envelopes will greatly increase V2G power. Australian consumers have led the world in DER uptake to date, solar and batteries, and the same consumer sentiment could apply up to V2G technologies. Australia's pioneering small-scale inverter grid connection standards supports high levels of inverter-based distributed generation in the power system. Unlike other new energy technologies, we expect uptake to be initially limited to early adopters and for this to expand into a broader market as industry mitigates product and integration costs and complexities. While there is some uncertainty in the timing of mass market uptake, it is clear that individual EV owners, there'll be some definitely value for individual EV owners for the next 2 years and ultimately the whole system. The same way, we've got feed-in tariffs in the early days, very beneficial for those who took that on board. And now I guess through, smart electricity plans that help home battery storage for people who have them. So the challenge for Australia is to establish an effective framework. Marginal cost is low. I can expect capital costs in the order of $25,000 per megawatt hour, or 6% of current large-scale battery costs, which is around $400,000 per megawatt hour at the moment, because as we said, the car has already got the battery at home on a similar. So it's quite cost-effective, really. The basis of this advantage is that the cost of enable V2G is only a marginal increase in the cost of installing a V2G. The batteries in the car. This seems to be the recurring theme, and I like that. It's already in the car. So despite the size of the prize, no Australian jurisdiction has policies or programs designed to promote V2G in our fleet already, which is a shame. This is what this report is about. Understandable given the nascent state of vehicle and equipment supply chains. However, the headline from our analysis that this will change quickly over the next 2 years, and it is time for Australian governments and regulators to get the skates on, prepare the policy and regulatory frameworks and industry support for infrastructure that will enable the benefits of V2G to be realised. Yeah, that's can't say it any stronger, really. It's very cost effective. Makes sense. Okay, so customer value of V2G. All right, so the next few pages really, I won't go too much into it because it's just lots of tables which show how beneficial having a V2G with dynamic pricing is for customers across all the NEM markets across Australia. So from ACT, New South Wales, Queensland, South Australia, Tasmania, Victoria. It just makes sense because you can see the modelling there from a convenience charging and time of use to smart and time of use, smart with dynamic pricing, V2G and time of use, and the best usage for the customer from a cost point of view is V2G and dynamic pricing. So they seem to have modelled it, and it makes sense to have that available for customers in the future with EVs and V2G dynamic pricing. And then more on the distribution networks as well, how it can be useful to get them on board, and getting the NEM market settings right. And there's an example of the Nissan Leaf with a V2G enabled system at home, or EVSE. Okay, and some appendices here. So again, more modeling approaches there for the different markets. And some more pricing sort of modeling there. So for example here, bidirectional charger, yes, will be more expensive, 7.4 kilowatts at $5,000 compared to a convenience charger, which is half that price. EV charging constraints, so 60 kilowatt hour EV, which seems to be a good entry level kind of car these days, 50 to 60. Minimum battery state of charge, 40%. Losses energy, 7% energy losses to both EV and discharge cycle. 10-year modeling parameter, 80% price accuracy. Discount rate for future forecasts, future cash flows. So again, that's what they're kind of the parameters they use for their forecasting and modeling. Okay, so again, case study results showing that V2G and dynamic pricing makes the most sense, or one of the models that makes the most sense, together with probably smart and dynamic pricing. State by state, territory by territory. Let's keep going down here. So I won't go through each one, obviously. And they've got a case study for the Ford F-150 Lightning as well, using their Ford Charge Station Pro. So we'll just go through this quickly. So with the Ford Lightning F-150, Ford offers the EVSE to suit the car. The EVSE is connected electrically, communicates with the supplied home integration system, comprising of a bidirectional DC to AC compliant inverter with local wiring codes. Inverter is not grid synchronized at this stage. And switching from mains to backup power is automated, managed by the home integration system. Backup power is large, so 9.6 kilowatt up to 151 kilowatt hours. That's huge. That's a huge battery size suited to electrified homes, and you need that if you're going to have an EV at home running basically everything electric, from heating to cooking to hot water. Power transfer capacity is limited by the capacity of the inverter. On the DC side of the inverter has a DC bus to connect DC power sources common to residential settings, such as solar, PV, stationary batteries. So all certified, tested by Ford, dedicated sales channel using an approved partner, and this model is readily replicable in Australia, subject to other issues of EVSE testing and certification. So, yep, that's one case study there. And then more appendices on long-term battery fleet gigawatt hour estimates. So EV uptake in different market segments, future battery technology improvements, and market pressures as well. More appendix and then more references there as well. All right, so there's I guess, how long was that? Yeah, that was maybe, I don't know, half an hour, maybe longer. I've lost track. Walkthrough of the V2X summary report from ARENA. And it looks like, based on their modeling and based on their justification for the numbers they used, it makes a lot of sense. We need the energy storage, no doubt, if we're going to electrify things to make things more sustainable. And the most cost-effective way they can think of keeping that storage or using the storage that's already there if we change to electric vehicles by 2050 is the battery is already in the car. It's going to be 6% of the cost required to basically have stationary storage, like a stationary battery pack or power packs. So yeah, interesting times ahead. Let me know what you guys think. If you've read this report for yourselves or heard anything else, please leave a comment below as well. I'm always learning myself too, so hopefully we can all learn together. Otherwise, thanks for watching, and until the next Ludicrous Feed video, happy charging, everyone.